I'm Dalton Harris, and this is the Double Tower of Hanoi. The Tower of Hanoi is a tower that is placed on a rod, we'll call it A, and there are two other rods, B and C, and the goal is to move the tower from A to C in as few moves as possible, and without letting a larger disk be on top of a smaller disk. The problem I have is a double tower of Hanoi contains two end disks in different sizes, two of each size. As usual, we're required to move only one disk at a time without putting a larger over a smaller one. How many moves does it take to transfer a double tower from one peg to another if disks of equal size are indistinguishable from each other? What if we are required to reproduce the original top to bottom order of all the equal sized disks in the final arrangement? What we know. As we've done in class, a tower of Hanoi with n disks and n different sizes requires 2 to the n minus 1 steps to move from pole A to pole C, with pole B being a pivot, assuming a larger disk cannot be placed on a smaller disk. So if n is 1, that means you have one disk, one size, steps required is 1. If you have n is 2, that means you have two different size disks, still two disks though, steps required is 3. If you have n is 3, you have three different size disks, and the steps required is 7. Approaching the problem, there are n disk sizes with two n disks. When n equals 1, this means that you have one size disk, but you have two disks because 2n. This will only take two moves. Obviously, you have two disks, and then it doesn't matter if they stack on top of each other. When n equals 2, you have it requires 6 moves to move the two different size disks over to pole C without the smaller red ones getting crushed by the blue ones. When n equals 3, it requires 14 moves to move all of them over to the pole C, assuming that you don't crush any of the smaller ones with the larger blocks. To the side of all of these, you can see the steps taken to move it over. If you compare the original Tower of Hanoi to the double, you'll notice that the steps required is just simply double. What the original tower required is that actually what it is. If the steps required to solve a double tower appear to be 2 times that of a single tower, let's try it. So what we're going to do is we're going to multiply 2 by the original equation for the Tower of Hanoi, and what we get is 2 to the n plus 1 minus 2. We're going to plug that into our equation over here, or we're going to put that in our equation over here. We're going to plug in n into the equation, so we're going to get 2 to the 2 minus 2, which is 4 minus 2 is 2. That does check out. We'll do it again here, just for the sake of doing it. 2 to the third is 8 minus 2 is 6. I can assure you that the rest are also correct. So it appears that this equation does work as long as n is greater than or equal to 1. It will not work for 0, obviously, because you'll have 0 disks, 0 sizes, 0 moves to be made. So the second part of the problem, refresher, how many steps would it take if we were required to reproduce the original top to bottom order of all the equal sized disks in the final arrangement? So basically what we're going to do is reproduce part A with the disks in the same order that they started out. So something that I noticed as I was working through part A was that all the disks were in the right order except for the two largest disks, and this was just because they didn't move until they were ready to be moved over to C, which puts the top of the two larger disks on the bottom and the bottom one on top. So what we're going to try to do now is figure out an equation that that puts all of them in the correct order. The steps to move from pole A to pole C. The first parts are not too hard, but once n equals 3 came into place, things got a little more complicated, a lot more steps. Just got a little more tedious. I did these out in person with quarters, nickels, and pennies. I labeled each one of them 1 through 4, stacked them up on the table, and proceeded to move them around until I figured out the number of steps it took. So the number of disks, not including the two largest, is 2n minus 2. We're going to be referring to this later. All this means is all the disks other than the two largest disks fall under the category of 2n minus 2. So that is useful because the equation to move the 2n minus 2 disks from one peg to another, regardless of order, is 2 to the n minus 2. This stays true for all of them. For example, I know off the top of my head, when it's 3, it requires 6 moves to move the top two and the middle two disks from uh, pole A to pole C, and vice versa. It doesn't really matter. It just takes 6 steps. We'll refer to the 2 to the n minus 2 equation as dn minus 1. Demonstrating the formula. So I put together this video of how to, oops, why is it starting back there? I put together this video to give you a visual representation of how to move the disks, 2 n disks, from pole A to pole C while maintaining the original order of 1, 2, 1, 2, 1, 2. If you remember, dn minus 1 equals 2 to the n minus 2. All this is saying basically is that's the number of steps required to move these top 2 disks over to pole C, regardless of order. So we're going to start the video. I move the top 2 disks to B, the medium-sized disks to C, and then the top disks, or the smaller disks, excuse me, to pole D. Now I move the larger disks to pole B. These are just going to be +2 because it's always going to be +2 regardless of how many size disks you have, as long as you have your +2 and then the movement of all the other disks combined, which is dn minus 1. We have that +2. And then again, we're going to move dn minus 1 is all going to be over here. We're going to move the small 2n disks, 2n minus 2 disks, excuse me, all the way over to pole A. So we have that right here, and then we're going to move the larger disks over there, which are in the right order. Now, if you'll notice, we can't just move all of these disks over there. We have to rearrange the order so that the 2's are on bottom. We're going to refer to this as Cn minus 1. That's basically just the number of steps to move the 2n minus 2 disks from pole A to pole C while maintaining the same order. I believe it is 11 steps right here. Made a little mess up. That first step didn't count, so that's 2. And that's 3, 4, and there we go. Total of 27 steps taken. So now we're going to end up solving the equation. We have this 2 to the n minus 2. All these are going to end up canceling, and we're going to end up getting 2 to the n plus 1 plus c n minus 1, and we're going to start working backwards, adding the previous terms and subtracting the previous terms. And then this is the summation that we have, and we're going to plug in n minus 1 for this k, and so we will get c, these n's, the n minus n will cancel, and we'll be left with a double negative 1's, which will just be a 1, added to the summation of this n will also cancel with this, so we will have a positive 2 minus a negative 1, which will end up being 3, and minus n plus 1 on top, 2 to the x, and we do know that c1 equals the base case, or is the base case, which equals 3, which is what we have here. And unfortunately, that is as far as I've been able to solve. I'm not exactly sure where I'm supposed to go next, but I do know that the final equation is Cn equals 2 to the n plus 2 minus 5.